Hi everyone, Mr. Boltri here, bringing you video 4.1. We're going to be talking about momentum. So in this video, we're going to talk about what is momentum and then connect momentum to something that we've already talked about, Newton's second law. So first of all, what is momentum? Well, you've probably heard momentum before. Used in kind of a cultural setting, and it means something a little bit different in a cultural setting than it does to a physics class. So how you've maybe heard it before, this is a definition I pulled from the dictionary, not the physics dictionary, is it's defined as the strength or force gained by motion or by a series of events. So you might have heard this, for example, in a sporting context. For example, if one team just gets touchdown after touchdown after touchdown after touchdown, 4 touchdowns in a row, you might say like, whoa, they have all the momentum, meaning that the sort of, they are moving fast, they are going to be hard to stop, hard to overcome, there's going to have to be something really big that happens for the game to swing against their favor. But in a physics setting, momentum is actually often called the inertia of motion. So it means something kind of similar as how we use it in a cultural setting, but it has a more specific definition. And specifically, let's remember that inertia is a property of matter whereby it maintains a constant velocity unless acted on by an unbalanced force. So if an object is at rest, it will stay at rest. If an object is in motion, it will stay in motion at a constant velocity. And so then momentum, this is all just a complicated way to say momentum is a quantity that we can measure. It's just scientists have looked at this quantity and measured it and found interesting things about it. But it's basically, if you Google momentum in a physics context, you're going to just see basically this equation as the definition, because this is a quantity that is defined basically by its equation, and the equation is momentum, which is represented by the symbol lowercase p and is a vector, can be found by taking the mass of an object and multiplying it by its velocity. So you can sort of see that it has to have a velocity to have a non-zero momentum. And if it has a velocity then and a mass, and all the objects we're going to be working with have mass, then it will have a momentum. So you can sort of see how it's related to inertia, because this velocity turns into the momentum, and we multiply by the mass, which is basically the how much the object wants to keep going in that same velocity. But this equation is worth noting because it is how we are going to calculate momentum. Momentum is basically defined by this equation. So you might be wondering, well, why do we use a lowercase p and not like an m or something? Well, the easiest definition is that m was already taken for mass. So then why do we use a lowercase p? Because uppercase p means power, and this lowercase rho means density. So why did they choose the simple p for momentum? And the best definition, the best explanation that I can find for this is that there's a Latin word, petare, which means to go to. And since momentum is all about velocity and going towards something and just continuing to move, they used p petare for momentum. That's just kind of the way it's going to be. We need to definitely solidify in our mind the difference between these three: a capital P, lowercase rho, which looks a lot like a lowercase p, and actual lowercase p, which stands for momentum. So just something to keep in mind. The useful thing about this is the momentum is the vector of the three. So that works out pretty well for us. Anyway, how is this all connected to Newton's second law? Because they are really connected, and the connection is kind of interesting, so I want to show you how. So first, let's just remember what is Newton's second law. And we know that this net force is equal to the mass times the acceleration of the object. Because remember, unbalanced net force, which is a non-zero, or unbalanced force, which is a non-zero net force, is going to cause an acceleration. That is this is a quantification of Newton's second law in the form of an equation. We know that acceleration is just a change in velocity over a change in time. So we can rewrite this as a change in velocity over a change in time, replace that acceleration, and a change in velocity is going to be a final velocity minus an initial velocity. So if we distribute the mass to the final velocity and the initial velocity, hopefully you see where this is going. Mass times velocity is just this term that we've just talked about, which is momentum. So we can say the net force equals the final momentum minus the initial momentum divided by the change in time, or just the change in momentum divided by the change in time. So I know these two equations look a little bit dissimilar, but they are actually identical, just using kind of a variable substitution and the definition of momentum that we just talked about. So why is this relevant? Why is this important? Because, well, the first thing is it allows us to solve for different quantities depending on what we're given in the problem. But also more importantly is we've always learned that this net force equals mass times acceleration is Newton's second law. And it is because these two things are identical, but this is actually not the way that Newton originally wrote his second law. He wrote and discovered his second law in terms of momentum. And just so that we don't have to teach an additional concept of momentum in order for you to understand Newton's second law, we teach it this way, but this is actually the way that he discovered it and wrote it originally. Well, I say that, but he didn't actually write it exactly like this, because remember, Newton was the guy, or one of the guys, who was super involved in the creation of calculus. So he took this one tiny step further, which he said, well, what if we take this delta t, which is a time interval, and we made that time interval smaller and smaller and smaller and smaller and smaller, such that it was basically 0 seconds. So if we found the rate at which the momentum was changing at any given instant, which is, we know, the derivative of momentum with respect to time. So when we take this delta t and make it really, 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 really small, it's basically taking the derivative of the momentum with respect to time. So if you actually look in Newton's original work, he says, translated, the rate of change in momentum of a body is directly proportional to the net force acting on it. So rate of change momentum, that's just the derivative, and he doesn't say, but it's implied with respect to time. So the derivative with respect to time of the momentum equals the net force. And the direction of the change of momentum takes place in the direction of the change of net force, which is why we put the vector symbols on these. So it's basically saying the exact same thing, because momentum is just mass times velocity. And the velocity changing with respect to time is going to be an acceleration. So basically net force equals mass times acceleration, but just written differently. And this formula is really powerful and allows us to solve for a lot of different problems and a lot of different quantities, which I'm looking forward to doing with you in our next class. But for now, this is Mr. Boltri wrapping up video 4.1 on momentum, and go Bears.